I'm going to try to do this without a mic. I practice yelling at children, so I can raise my voice quite dramatically when I want to. But I won't yell at you. My name is Rick Ostfeld. I am a senior scientist here at the Cary Institute, and I am standing in for Cary President Josh Ginsberg, who is putting on his other hat, his scientific hat, the one he wears sometimes while he's being Cary President, when he has two hats on at once. He is now down at an international conservation biology meeting in Cartagena, Colombia, so he couldn't be here and asked me to do the introduction tonight. We have a lot of return visitors to Friday night at Cary, and so I presume that many of you have been here before. In case some of you have not and are here at the Cary Institute for the first time, a very brief introduction to what the Cary Institute is beyond the Friday night events that we have periodically throughout the year. So the Cary Institute is an independent, not-for-profit, private environmental research and education organization. And we are investigating through various members of our scientific and educational staffs things like how to make cities more sustainable, the status of fresh waters worldwide, the future of northeastern forests, and the ecology of infectious disease, about which we're going to hear more in just a moment. I wanted to take a moment before introducing tonight's speaker to point out that the ideal seats in the auditorium have these little tents, these little name tag things above them. They're not right in the front, because sometimes people don't want to sit right in the front row. I don't know why. And they're not too far in the back. Those seats are for members of the Aldo Leopold Society. This is a group that makes events like this possible by providing support for the Cary Institute. And so I would like to give a special thanks to members of the Aldo Leopold Society who are here tonight, and also to tell you that if you are interested in finding out more about it and potentially joining the Aldo Leopold Society, there's information out in the lobby on the table. Or if you prefer a human being to stacks of information on tables, Olivia Van Mellekamp is in the back of the room waving her arm in the red. She is the human being that you can talk to afterwards about Aldo Leopold Society. So there are two quick announcements then about upcoming future events that I also have to attend to, that I need to mention. On Friday, April 18th, Philip Duffy, who is the president of the Woods Hole Research Center in Woods Hole, Massachusetts, will be speaking on what I find a very provocative and compelling topic. His title is Climate Change: How to Make Progress in an Era of Alternative Facts. So that one might be appropriate to attend.
August
Friday,
18.
that is August 18th. August 18th. Then on Friday, September 8th, did I misspeak?
Yes.
Oh, I'm so sorry. It was an alternative fact. Friday, August 18th, Philip Duffy. On Friday, September 8th, journalist Andrew Revkin will be speaking on the topic of lessons learned and unlearned in 30 years of reporting on climate change from the North Pole to the Vatican. Andrew Revkin was one of the world's leading reporters, scientific journalists on the topic of climate change and other environmental issues for the New York Times for more than 2 decades, and is now at ProPublica. So, on to the fun part of the evening. So it's a great pleasure and honor to introduce Shannon LaDeau, who is a member of the scientific staff here at the Cary Institute. A brief bio: her pedigree is that, part of her pedigree, she hails from Vermont originally. She got her bachelor's degree from Mount Holyoke College in Massachusetts, and then got her PhD degree from Duke University in 2000. most people are fine doing one postdoctoral fellowship at a time. Shannon did two at the same time. One of them was at the Ohio State University and the other at the Smithsonian Institution in Washington, D.C. At Ohio State, she focused on bioinformatics. At the Smithsonian, she focused on the biology and ecology of birds and bird diseases. So that represents both the quantitative number crunching chops that she has and also the biological, natural history, organismal chops that she has at the same time, which is an increasingly rare combination. After those two postdocs that she did at the same time, I don't know how she pulled that off, she came to the Cary Institute in 2008, where she has risen up through the ranks to associate scientist level, which is what she is today. And she has emerged and continues to emerge as a leader at the Cary Institute and among our scientific staff. So she has very broad interests in many aspects of the field of ecology. She's done seminal work on the effects of increasing carbon dioxide concentrations and climate warming on forest trees. She has worked aggressively to understand how forest pests and pathogens are affecting our ecosystems locally and regionally. She's worked on how West-Nile virus affects birds in North America. And she's worked on the threat of urban mosquito-borne diseases, which I think we're going to hear about more tonight, which is really integrative research linking both ecology and other natural sciences to very important social science aspects. Her title is The World's Deadliest Animal. Please join me in welcoming Shannon.
Thank you all for coming. It's really motivating and inspiring to see so many people come out on a Friday night to hear about mosquitoes. And thank you for that introduction. Always sound better introductions than what I remember. But so I'm going to jump right into this. So we make the claim with the title "World's Deadliest Animals," and I don't have to. Conveniently, Bill Gates has already defended that for me. So this is a graphic that Bill Gates produced on his blog. And it's based on data from the 2015. And basically, these circles are scaled to the number of deaths, human deaths, caused by different animals. And you can see that the biggest circle is mosquitoes, 830,000 deaths a year. I'll point out that in a fairly close second would be humans killing humans. And things that we tend to think of as being super scary are actually pretty small dogs. Sharks, lions are in here somewhere. I mean, I haven't been too scared of lions lately, but there's a bunch of things in here that probably cause more fear if you're going to a place that has lions or you're swimming in the ocean with sharks, and yet they really are pretty minimal. And of course, the risk of mosquito-borne illness and death is not equitable across the globe, and so these numbers really are for the global population of humans, and not specific certainly to the U.S. or northeastern U.S. And then the leading cause of deaths in a given year by mosquitoes is by malaria, a protozoa that causes severe illness. Currently endemic in 91 countries. Yellow fever is the next. So these are the three leading causes of mosquito-borne deaths in a given year, although they're not the only. Yellow fever and dengue virus are two viruses that also cause more morbidity, more illness than death. And so the death rates are a little lower, but the case numbers are huge. And in dengue virus, the case numbers are actually growing. People don't die, but they get very ill, and sometimes that illness, they can die, but it's not as common as malaria. So just a little bit about mosquito ecology. There are 3,500 different species of mosquitoes that have been recorded. That's across the globe. And there are 41 different genera, so different groups of related species. There's about 70 species in New York State. And all the species have a few things in common, and one is that they have an aquatic larval juvenile stage. So mosquitoes lay eggs, and sometimes they lay eggs on dry surfaces, and sometimes they lay eggs on the water itself. Those eggs develop, and they have to survive in water, where they feed, and where most of the population regulation naturally occurs. And so things eat them while they're in the water. They grow at rates dependent on what they get to eat in the water. They compete with other species of mosquitoes for things to eat and to get away from predators. So a lot of the community ecology and population ecology that determines who gets to be an adult mosquito it happens in this aquatic phase. And then they pupate and emerge. So this is kind of like their cocoon where they grow wings, they emerge, and for the male, the only thing they ever eat is plant nectar. And for the female, for most of their life, they survive on plant nectar. And so they're actually pollinators. We, of course, don't notice them until they are blood-sucking females that need to get a blood meal in order to produce eggs. And they don't just bite humans. So even of those 70 species that we might find in New York, only a handful bite humans, and most of those don't do it in a targeted fashion. But they'll bite birds and frogs and snakes and other small mammals. And you have some mosquitoes that do only bite certain taxa. And so you have some mosquitoes that really only go after cold-blooded animals. And you can imagine, so mosquitoes are keying in on CO2 and temperature, pheromones, and so they have specialized, some of them have specialized to really just key in on certain animals. Similarly, some that feed on birds, when they're searching for a blood meal, they're doing it in the trees. So they're not doing it down at the ground. So they're more likely to feed on birds because that's what they're looking around. So they have a broad ecology both in habitat and in behavior that really influences whether or not they're a problem to us. So back to malaria, again, that leading cause and the reason that we call mosquitoes the deadliest animal. There are over 200 million cases a year that result in 700,000 to 800,000 deaths a year. 70% of those deaths are in children under 5, and 90% of them are in Africa. But this is true. So malaria is transmitted by the genus Anopheles. So it's one group of mosquitoes. It's about 40 different species of Anopheles that are able to transmit malaria. And we have one of the species here. This is the range map in the US. Anopheles quadrimaculatus is a common vector. You could walk outside in our woods right now and get hit by this mosquito. And in fact, in the past, we've had malaria outbreaks in the US. European settlers in the West African slave trade brought malaria to the United States, and Native Americans were sickened with malaria as well as other things that were brought over. And this is a map from the 1930s of malaria activity in the 1930s. And returning service men and women in both World War I and World War II were exposed to malaria and yellow fever overseas and brought it back into the US, again, to places where we already had the vector. And these are data on cases from 1932 up to, I think this is 1950 or close to it. And you can see there were a lot of cases of malaria in the early part of the last century. And there's a huge, these are in these states that had endemic malaria going on still, and there's a huge bump during World War II as people brought in more malaria. So malaria doesn't move around in mosquitoes, it moves around in people who are sick. And then it was eradicated in the 50s and from the US. And it was eradicated both because of amazing chemical advances, which have been around for a while, but were targeted at mosquitoes in the 40s. And DDT was a very effective insecticide. It had many negative impacts on the environment that weren't known at this time because it's so, for the same reasons that made it so effective. It's really effective because you can spray it all over plants in houses and places where mosquitoes hang out, important tool targeted at eradicating mosquitoes, and it is very responsible for why we do not have malaria and yellow fever into the 60s and 70s in the US. And the other thing that happened in the 50s was suburbia. We got a change in the housing development, and these houses would have all been built with screens. So it was the first time you kind of get a bunch of very uniform houses and screens spread throughout large parts of the population of the US. And so again, you're separating the humans from that biting activity in a way that hadn't really been done in an organized way before. So, however, we still have had 63 locally transmitted. That means that a mosquito in the US bit somebody who had malaria and was able to give it to somebody else in the US. 63 locally transmitted outbreaks. These are small clusters, a few cases or one, throughout the US between 1957 and 2011. So it's not completely without risk, because we have the vectors here, they're here. And so when people come in at the right time, in the right kind of numbers, and they've been to a place that has malaria, and maybe they have a malarial infection, it can be transmitted locally. But what we really worry about more these days is the emergent viruses that are coming in that are mosquito-borne. And west-nile virus is one example that I think most people in the audience are probably familiar with. So it came into the US in 1999. It's one of the arthropod-borne viruses, so an arbovirus, a virus that is transmitted by an insect vector that has a zoonotic host, and the virus actually can't build up in the human. It has to build up in the zoonotic host, the animal, non-human animal host. The mosquito has to pick it up from that animal, in this case a bird, and then give it to a human. And so West Nile virus is pretty complicated. In order to get it to a human, you have to go through a series of ecological populations. That means a mosquito has to bite a bird and then survive long enough to need to reproduce again and bite a human. And so that's a pretty low probability event. And so when West Nile virus showed up in 1999 in New York City and quickly moved into Westchester, so the red cases here are counties with West Nile virus in humans, and the blue are counties where it's been detected in mosquitoes and birds. There was a lot of spraying that went into effect. They tried to kill off the culex, the mosquito population that winter, in hopes that it would come back again. This is a very complicated or complex system to get West Nile virus into the human population. And yet in 2000 it spread, 2001, 2, 3, 4. So in 5 years, this complex disease ecology system has spread across the nation. And you start to see a lot of white back here because they just stopped testing. This is here the bird flu, the made-for-TV movie about bird flu came out. And bird flu was a big scare. So a lot of the testing money actually got shifted over to bird flu surveillance. But you can see it move across the country really rapidly. In 2016, and now I'm not showing you by county, but every state in continental US, except for Maine, had West Nile virus activity detected, and Vermont, New Hampshire had it detected in birds and mosquitoes, but not humans. So it's still present. So it has shown up, and it pops up every few years with large case numbers, relatively large case numbers. But this is one that requires that zoonotic host, so it's going to be very difficult to get rid of, but it's also very difficult to get into the humans. And so it doesn't tend to have the epidemic outbreaks that we might see in a disease that doesn't require a zoonotic host, like dengue virus, Chikungunya virus, and Zika virus. These outbreaks, they've all emerged in the US, and dengue virus is now pre-endemic in parts of southern Florida. Chikungunya virus in 2013 first showed up in the Caribbean, and now pops up now and then, but was in Texas as well as Florida. There are And those viruses all have moved from this. So all of these kind of arboviruses that I'm going to mention, as well as malaria, the protozoa pathogen, originally would have evolved from this kind of zoonotic host system. But there's something about them that has adapted to the human system. And so they no longer need the non-human animal. They can build up in the human to high enough levels that a mosquito can pick up the infection. So with West Nile virus, we can get the infection, but it never builds up in our blood enough to reinfect the mosquito. So there's a handful of things that have evolved to do that. And all of the red ones here have evolved to do it in Aedes species. So this is a genus of mosquitoes, Aedes. There's a lot of different Aedes, but actually 2 Aedes species have really been responsible for the spread of all of these pathogens that are in red, these viral pathogens. And the 2 are Aedes aegypti, the yellow fever mosquito. This is one that was eradicated from the US with DDT by the 70s, but has moved back in. You can see this is the range of Aedes albopictus right now, where dark is you would find more albopictus, blue you wouldn't find albopictus. I put this one up here to remind me to say it's very much not cold tolerant. Right? This one does not overwinter here. Whereas Aedes albopictus, the tiger mosquito, is a newer, so this one's been around for hundreds of years, probably also came with the slave trade. This tiger mosquito has only been around since the 80s, and it's moved across the globe, out of Asia, and it's now establishing very well in very temperate regions, and so it's not controlled as much by winter climate, although it does still seem to be a little, we don't have any overwintering here yet. Okay, so there's still a northern limit, but it seems to be much more tolerant and adaptable to more temperate areas than Aedes aegypti. We'll deal with that when that happens. Sorry, it's doing something on here. Its native range. It was a sylvatic species, and so it actually would lay its eggs, which it lays on dry surfaces inside tree holes. So sylvatic, so it's in forests in Asia. And it wasn't really a problem in Asia. It tended to feed on small mammals and bring in things like bamboo. But in the 80s, the US started importing a lot more tires from Asia. And so the tire manufacturing built up in Asia. They would store the tires near the forest, and then the mosquitoes started laying their eggs in the tires, and those eggs can live for months without getting wet. And so that's how we have albopictus in the US, as well as across much of the globe. So albopictus is spread out, and it does very well in tires, but it also does really well in other things that are tiny and hold water, because it's used to breeding in very tiny bodies of water and bamboo. And this is a map in the US, and this, so we have albopictus in New York City, but it doesn't, and it comes up into Westchester a little bit, but it doesn't seem to overwinter further north than that yet. Likewise, you can see it pops up in some of the urban areas along the coast north of New York City, and it's been detected north of that 1 year, but it's not overwintering there yet. So it's still being controlled somewhat by winter climate. We don't know exactly what about winter climate, right? You can freeze the eggs it overwinters as an egg. Those dry, tolerant eggs. You can freeze them in the lab and they don't seem to all die. So this is a big topic for research right now. How do they overwinter? What are the actual climatic impacts that are regulating this population? It also doesn't do that well in real heat and drought. So Aedes aegypti still does better in Florida, but it's moving fast and it seems to be adapting quite quickly. Okay, so Chikungunya virus, which is one of the viruses that both Aedes albopictus and Aegypti can transmit. This is a model that came out in 2006 before Chikungunya virus moved around the world. It was it had moved a little bit into some areas where it had shown the ability to adapt to albopictus, so that it would be transmitted more efficiently by the tiger mosquito. But predominantly, most of the chikungunya cases were still transmitted in places where you had the yellow fever mosquito. And so these folks did a prediction that you might see chikungunya movement into all the places where you knew Aegypti and albopictus could be across the globe. And then it actually did move there. So it's not very often we get to make predictions and then see them come true. And this isn't one that you want to cheer for, but it came true. So we have it moved into the Caribbean and then up into Florida and Texas and the US. What did get here though is the version of the virus that is adapted to the yellow fever mosquito. So far we're lucky because it's not the albopictus version, which got to France and Italy and caused large-scale outbreaks of chikungunya virus there. Chikungunya virus is similar to west-nile virus in that it causes febrile illness, flu. It actually affects more people. So 80% of people who get west-nile virus probably don't get any noticeable symptoms, but most people do get noticeable symptoms with chikungunya, and it can last for a long time, but it does not have a high mortality rate. So if the vector's there, these pathogens are likely to show up. So that is the albopictus in Italy and France, the Mediterranean area. And then this was a model that came out last year looking at Zika virus risk. And these guys did it based on Aegypti only, the yellow fever mosquito, although there is plenty of evidence that albopictus is a competent vector, meaning it can both pick up the infection and pass it on. And you can see New York City pops up here as a huge possible risk for Zika. And the reason it does is that these circles are scaled by the number of people that are coming in from other places where you know Zika is active. So the number of people that are coming in this case from South and Central America, into New York and to Miami and Houston make all these very large circles. And then the high risk, the high abundance of albopictus. So from this map, you would suggest that Miami would be the first place you would expect to see Zika outbreaks. And in fact, we saw Zika outbreaks that year in Miami, but we also saw them in Brownville, Texas. And we know that these are the Zika cases that year from all across the country, and so more blue is more cases, right? So almost every state had people coming in with active Zika infection. And yet we only saw it in Brownville, Texas and Miami, and we expected to see it in Miami, but it's still a mystery why Brownville, Texas. And so part of this is here because there's some random reason why some places end up having these outbreaks and others don't. Somebody had to come in with active Zika infection to the right place when the vector population was high, and then they had to be outside long enough to get bit. These mosquitoes bite during the day. They're not the kind that are creeping in your house at night and biting while you sleep. So people had to be spending time outdoors in a place where they got bit. And then once that happens, it can take off. And so Brownville, Texas is actually still on the watch list, recommending that pregnant women don't go there. All right, so how do we define a managed risk? So that was kind of a little introduction. If we took this at face value, then we all just did the riskiest thing we're going to do today, which is walk across the parking lot where there are no mosquitoes into a room full of people. Because humans and mosquitoes are the riskiest things, right? But we also know that where you're at matters, and so in mosquito-borne disease, risk is related to the probability that the mosquito is going to get infected. That means it sees somebody or an animal that has an infection, and it's able to pick that infection up. And so somebody who was infected with Zika could be bit by 5 different species of mosquitoes, and only one of them might be able to actually pick up the infection and allow it to replicate in its gut, right? The viral infection has to actually live inside the mosquito for a little while before that mosquito can pass it on. So it has to both become infected after the salivary glands, right? This is the reason why we don't tend to worry about HIV being passed from a mosquito biting one person to another, because that the HIV doesn't survive in the mosquito, and mosquito is not just a hypodermic needle moving from one person to another. There's life history stuff going on in between, and that actually controls a lot of the vector transmission. We don't know a lot about mosquito survival in the wild. It's very difficult to see how long mosquito survives. They're very, very tricky to mark and recapture. People have tried, and it turns out so we've got research right now that we're trying to look at this in the field. It's very different than what happens in the lab. But it's a really important component of understanding why risk might vary from one area to another. We just don't know a lot about it. Anopheles, for instance, malaria, has to survive for almost a month from the time it picks up the malaria protozoa to the time it can pass it on. So that's one reason why we really don't, even if somebody infected with malaria came here and sat in the village of Anopheles and got bit, it's very unlikely that any of those mosquitoes are going to survive long enough because our season isn't that long. And then biting behavior, right? So if mosquitoes bite a person and then bite a cat, we don't worry about it. The cat's not going to get infected with most of the same viruses. The mosquito's not. It's a dead end. The same reason why if a mosquito bites us with west-nile virus, it's considered a dead end. We don't make enough west-nile virus to then reinfect the mosquito. So what mosquito bites matters. And different species, as I said, focus on different things, and some species focus on whatever is most abundant and close by. But that behavior is very important for understanding risk. So in order to kind of flesh that out and give a little picture of what I mean, I'm going to talk about some work I've done in Baltimore, Maryland. In Baltimore, Maryland, of course, is in the mid-Atlantic. It's a trade and travel hub, so it's a place where you get a lot of people coming in, both with Baltimore as well as the entire mid-Atlantic megalopolis there. It also has a lot of variation across neighborhoods, so we could really use this city to try to understand some of those spatial causes of why you might get pop-ups in one part of Brownville or one part of Miami and not, a mile away. There's also a lot of environmental justice issues that are very poignant in Baltimore with race and disinvestment in infrastructure and poverty that made it a very interesting place to look at mosquito dynamics, as well as the fact that it is a place where you get Aedes albopictus, the higher mosquito in high abundances, as well as the west-nile virus vectors. And I can't say enough about the Baltimore Ecosystem Study, which is a National Science Foundation funded program that actually is run out of Cary Institute. So it was a good place for me to start working when I began my career here. And we work in Baltimore City in neighborhoods that, this is the median city income, about $41,000, and we've chosen neighborhoods that are above that median income, neighborhoods that are at the median income, so about $40,000, and neighborhoods that are well below it. And then within the neighborhoods, all the neighborhoods have blocks with row homes, and so we have very similar infrastructure within each of these neighborhoods, and they're about at the maximum 2 kilometers apart. So they're pretty close, and so we get the same climate, the same biological background here, but very different human conditions. And just to kind of put a face on those human conditions, even life expectancy varies at this scale. So life expectancy, this is all the Baltimore neighborhoods, and this yellow is the neighborhoods where we work, goes from about 67 years. In 2014, somebody born in these neighborhoods over here had a life expectancy of about 67 years versus almost 90 years up in the darker red. So I think that just wraps up a lot about these neighborhoods and the kinds of issues that are going on there. And then to take a visual approach, this is a neighborhood that's at that median level. This is a block within it, and this is a block that's well below the median level. And you can see they both have trees. It's not just are they green, are they not green? They're both actually quite green. They both have grassy lots. In the median income neighborhood, you're more likely to find this kind of yard where people have kind of fenced it off and planted grass, and they've kind of got some community organization around those grassy lots. And then lower income, below median income neighborhoods, you get, I don't know if you can see, these the low median income, so lower income neighborhoods, we find that there are more mosquitoes. These are adult females. We only look at females because they're the ones that bite. And these are traps that we set out, and we use CO2 to draw them in from, maybe 50 meters around. And then what you can see here are the differences in the outliers, the median number of mosquitoes, and kind of the 75% quartile. So this is over the entire season. So what we're really looking at is these outliers. You get huge numbers of mosquitoes, up to 300 a night, in some of these traps in the lower income. And when you get up to the higher income neighborhoods, you get fewer than 100. Just for reference, the current state mandate on when you have to actually go in and do something for Zika and for Zika management and surveillance is if you get more than 25 per night in the trap. So Baltimore has really high numbers of population of mosquitoes, even in the above median income neighborhoods. And then we wanted to know, does the fact that there are more mosquitoes mean that the risk is higher for poor people that are living in these lower income neighborhoods? And remember, this is a function of the vector abundance. We know that there are more mosquitoes there, but also of their biting behavior. Well, the next one would have been, sorry, is it? Okay, so what we do is we collect all those mosquitoes in our trap and we crush them up and we look at the DNA that was in their gut. And so we can see what they did. And most of them have nothing in their gut. But some of them have had a blood meal, and so we can look at the DNA from that blood and we see what they've been eating. And in lower income neighborhoods, they're predominantly eating rats. And these are scaled by the relative proportion. They're scaled by relative proportion. So they're predominantly eating rats here. In the above income neighborhood, they're predominantly eating humans. And we also see dogs and cats, and we see deer. Put that on here. We see a few. And in the above income neighborhood, we see birds pop up as well. And then we have to think about this in terms of, so that was relative, so one mosquito is more likely to bite a human in the higher income neighborhood, but there are far fewer mosquitoes, right? So risk becomes, it's a very complicated thing to think about how this manages risk, but even because there are so many, even though they focus on humans less in the lower income neighborhoods, right? So a mosquito is more likely to bite a rat than a human, there's still so many more mosquitoes there, that risk is actually still higher in those lower income neighborhoods. And it's actually probably highest in the median ones where you get a real mix of infrastructure and human occupancy. So we wanted to look at management strategies. And the first management strategy, the easiest one to think about, is you eliminate the breeding habitat. If there's no water, right? All mosquitoes depend on water to breed, and it has to stick around for at least a week. So you eliminate that, you can eliminate mosquitoes. Of course, other strategies include reducing the adult survival, and that has been the focus of many chemical advances, adulticides like DDT and new organophosphates that are very effective if you can hit the mosquito with them, as well as genetic engineering and different technological advances. And third, one of the things that's been such a benefit to the U.S. and to our quality of housing and living in the U.S. is limited access to humans makes a big difference. Certainly with anopheles, which like to bite at night, screens and sleeping indoors is enough to really knock out a malaria outbreak if it were to occur in the U.S. But we focused in on the first one, eliminating breeding habitat. And one of the reasons we did it is that we know from our data that if you have more unmanaged or trash containers, you actually got more female mosquitoes. So it would make sense that if you removed trash containers, you might get fewer. And so trash containers are different kinds of things that are discarded and unmanaged. So when it rains, they're wet. If it's dry for a long time, they're dry. Versus things people have in their yard and tend to think about and touch and dump. And so we went out and we went across several blocks in Baltimore. This is last year, and we're repeating it again this year. And we got adult abundances, and then we did our intervention and looked at how it changed. And we hoped for a decline thoughts about risk and bring it back home to New York and New York City. Up here, again, we don't really have the tiger mosquito up here yet. It'll be here. It's moving quickly, it shows up, and eventually it'll show up here. But right now we have the tiger mosquito. This is in New York, in the boroughs, and we have, this is a student that is at Columbia, who I worked with. Eliza Little did this work, and she got information from New York City pest management to find out where mosquito populations were, where they've been finding Aedes albopictus, and looked at the relative population. So Staten Island, big hotbed of Aedes albopictus outbreaks in New York right now, although you find them across Queens and Brooklyn as well as some of the other boroughs. Chikungunya in 2014, she looked at where chikungunya, those cases were coming in, and these are hard data to get. She had to work with the health department to get these, and a lot of those cases were coming in up here. And what you can see is that that doesn't necessarily overlap with the abundance of albopictus, which is really interesting. We don't know why yet. These are just data she was able to get and look at, and she's been doing more work to understand, why don't you get as many albopictus up here? But clearly, so when she looked at predicting what 2016 chikungunya outbreaks, where they were most likely, luckily they're not that likely across a lot of the city because you don't have that overlap of people coming in with chikungunya infection and the vector. And similarly with Zika, we can't, right now I don't have the data on where the Zika has been detected in people as they've come in. These are 2016 numbers by borough. 2017 to date, it seems like Zika numbers are down. But clearly, if people are coming in with Zika in different neighborhoods, the transmission potential expectations would vary, right? So if you've got a lot of Zika coming in where you don't have the vector, then it's not going to be a problem. But if they're coming in July in places like Staten Island, then you worry more. And so those are the kind of spatial things that have to come into play when thinking about risk, right? So risk depends on the presence of an infected person, and as well as vector abundance and biting behavior. But the variation in infrastructure and healthcare and human behavior that we see across a lot of the landscapes in the U.S. where people live actually play a big role in where you actually would expect these outbreaks to take hold. I don't think it takes a lot of imagination to know that some neighborhoods, people that live there are going to be less likely to complain about mosquitoes. They're going to be less likely to go and get tested if they do get sick. And so you're more likely to get outbreaks happening in some places where relative to others. And so right now, a lot of the control is very reaction-based, and so if they know that somebody tests positive for a virus, they will do a lot of control around where that person lives. And if people complain about mosquitoes in their yard or mosquito exposure, then control will focus on where people complain. But those don't necessarily align with what the models show us is where mosquito-borne disease and outbreaks are most likely. And so the effort in surveillance needs to embrace the idea or embrace some of the models that are coming out now and go beyond just where people are complaining the most about being exposed to mosquitoes, because there's a lot of populations that just aren't ever going to complain about mosquitoes. There are other things that are going on. But a lot of times those are the very places where things like albopictus are getting a hold, right? That's where they can get a hold and really establish as well as whatever viruses might come in. And with that, I have lots of people to thank, but especially for this crowd, Cary Institute, everyone who works here, all my colleagues and coworkers have been wonderful. And National Science Foundation has funded this work. The funding is actually over right now, so we're hoping to get more funding. But otherwise, it's been a great source of support for the work.
So there's time for some questions from the audience. I'm going to try to call on you from over here. So I think I saw that end first. Yes, please.
Hi, thank you so much for your presentation. It was excellent. Can you talk a little bit about the biting behavior in relation to time of day for the 70 species in New York? You mentioned the Aedes and Mosquito biting at night. How about some of the others?
So the question about biting behavior timing during the day, and they do have very different behaviors for when they are looking for a blood meal across the species and genuses. And so Anopheles tends to bite at night, at dawn dusk kind of time. Culex, which is the West Nile virus vector, is also a dawn dusk kind of species. The Aedes species tend to be during the day. So if you're like getting bit and it's sunny out and you're gardening at 10 in the morning, it's probably an Aedes. There are some other native species to the area that also bite during the day that come out after floods. Spring, they come out earlier in the spring after the ground gets wet, right? Like a lot of the species lay their eggs on the ground, and as soon as it gets wet, they come out, and many of those also bite during the day. So you can pretty much get bit all the time.
Yes, sir.
Yeah, two things. First of all, I was reading an article a while ago that the climate change is causing the Anopheles to migrate into areas that were never, in Africa, that were never affected. For instance, Nairobi is about 6,000 feet. And in that area, they had very little mosquito or malaria infection. Now the climate change is moving the mosquitoes up into those areas and it may do the same in the United States again. Of course, our southern states were mosquito and malaria infected in the early parts of the United States. Secondly, along the Amazon, there's areas that are either, I'm not sure whether it's acidic or alkaline, but those areas do not show mosquitoes. They're mosquitoes free actually, because the mosquitoes cannot breed in that type of an atmosphere, either acidic or alkaline. I'm not sure which one it was at this point.
Yeah, so two very good comments. One, the first about climate change. Yeah, there's definitely evidence that, that especially with elevation in Africa, but also in Hawaii, mosquitoes are moving further north. So whether they're moving away from heat below or they're moving because it's getting warmer in the Ken, there certainly is an expansion of exposure to Anopheles and other mosquitoes at higher elevations as they warm. And likewise, I would expect that mosquitoes that have previously been limited in the Northeast will continue to move north as winter temperatures change. And the comment about the quality, I don't know about the particular case with the Amazon, but the mosquito species have very different tolerances for water quality where they breed. And so the Anopheles species tend to need cleaner water, purer water sources, whereas things like Aedes albopictus can breed in small kind of dirty water, but even they can't take very high nutrient concentrations that Culex can. And so you get this gradient in where mosquitoes can breed and what they can tolerate. But there certainly are lots of places where the conditions would limit some of the species from breeding.
There's a question down at the end of the row. Yes, please.
Hi, you talked about having city planners and city management people accept the models that you are producing. How much data is there on the accuracy of those models?
Yeah, well, and so and the idea is more to, I said that kind of clumsily, but the idea is that we're at a point right now where mosquito control has been done a certain way for a long time, and it's not very well funded. And so we have people that try very hard with very little, and they rarely are just responsible for mosquitoes. They're responsible for pests and mouse. And so a lot of time it's reactive. And so the models are never going to be specific to a neighborhood, right? Like the brown bill Texas thing, it's never going to be predicted. But the idea that there's got to be something other than just responding to where people complain, because we know that behaviorally and socially and culturally, certain groups of people are more likely to call the government and complain about mosquitoes than others. And so not so much just the models, but go back to the first principles of what is the ecology behind where these vectors are breeding, and respond to that preemptively versus reactively.
Up here? Up here.
Sure, let's move to the back. Go ahead.
What is the average life expectancy of a mosquito?
So that's a really hard question.
But just an
Because-
average.
Yeah, I mean, so for the mosquitoes that people have studied, which tend to be the ones that try to kill us, it can really range. It's very temperature dependent. So as the temperature gets really hot, their life expectancy goes down. And it also tends to be influenced by what they bite. And so things that bite humans have slightly lower life expectancy because humans tend to swat and do things that kill them, versus things that focus on snakes. But a month, 2 weeks to a month, kind of would be but they live longer, and some of them certainly die much earlier than that.
Me too.
You mentioned DDT being used in the 60s and 70s. I'm curious, because we heard a lot about the spraying of mosquitoes in Miami because of Zika. What were they using, and what are the potential side effects of the, I guess, chemical that they were using?
Yeah, so I don't know exactly what they were using there, but there are some organophosphates and pyrethroid-based chemicals that are pretty effective, and some of them stick around for a little bit longer, not months like DDT. And so it depends on they still do adulticiding where they spray the air, but that doesn't tend to be that effective, and so it's not used that often because it has to hit the mosquitoes while they're flying around. And with Aedes, the vector, flying around during the day, and so nobody wants to spray while people are out. But so there are some other things that they'll spray down around bushes in places that will last a little bit longer. And something that kills mosquitoes is probably likely to kill other bugs. Like DDT, though, a lot of these things aren't known to have any effects on mammals until they DDT wasn't a problem until they found out it was kind of going up the food chain. But people weren't being affected by it, and so it's hard to know because the different, this little mealy mouth, but the different things that they use, most of them in the concentrations they use, they're supposed to break down pretty quickly, but they are targeting arthropods and insects, and so they'll kill mosquitoes, but they'll kill other insects as well. And many of them will also have bad impacts on aquatic organisms, so frogs and the local salamanders and things. They tend to, in Miami and places where they're using them, they're not spraying them in ponds. Yeah, they're spraying them under vegetation in places where the mosquitoes are resting. Likewise, when they use these same things in Brazil, a lot of times they're actually spraying the houses themselves and not the environment. But yeah, if you spray a pond, it's not going to have good impacts.
How effective is Bacillus thuringiensis against what species, and are there biocontrol methods being developed for mosquito species?
So I missed the beginning of the question.
How effective is Bacillus thuringiensis?
Right.
And against what types of mosquitoes, and are there biocontrol methodologies being developed for mosquitoes?
Yeah, and there are all the time. So BT is a bacterial component. Mosquitoes larvae. You put it in the aquatic habitat, it kills the larvae, they can emerge. And it's still very effective in the US. There are very few studies to show that it's not being tolerated increasingly in places where it's being used a lot. I mean, the research is still very effective, but it's usually done on populations that haven't been predisposed heavily in the field. So it's not clear how long it'll be effective. It's still also very difficult to use for Aedes because it's been used for Culex pipiens, the west-nile virus vector, which breeds in stormwater ponds and sewers. And so you go to some targeted areas and spread it versus Aedes, which breed in tiny little containers all over people's yard.
I'm going to go to the back here, and then we'll do one more after that. So show me if you really want to ask that last question. Yes.
Two-part. With diseases in humans such as hepatitis C and AIDS, why is it that mosquitoes cannot transfer from the blood of a person, a human, with one of those diseases? And the other part of the question has nothing to do with that. Does diatomaceous earth have any effect on eradicating? It's 100% natural. It shuts down the respiratory system of any bug.
So does what shuts down the respiratory system? I'm sorry.
Diatomaceous earth.
Okay, yeah, so the first part of the question, so mosquitoes have to take in the blood, and then they digest the blood, and the pathogen that was in that blood has to make it through their stomach, basically, and it has to survive their stomach, and then move back to their salivary glands before they can reinfect. So they actually, when they poke you, they're injecting salivary fluids that kind of numb and keep the blood running, but it's not the same tube as they're pulling blood back out, right? So they actually aren't going to inject you with the blood from anybody previously.
Oh.
So the only way you can get something from them is if that virus or protozoa has moved into their salivary glands to be part of that initial injection that will, which is why people have reactions, right? Like it gets itchy because they initially inject you with something to keep your capillaries open so that they can suck freely.
Well, I think it's a very
And some of them actually have analgesic, thank you, so that you don't feel it as well. And so that's why some people get big wells from certain mosquitoes, but not others, because they have slightly different chemistry. But that's also why some mosquito species have slightly different abilities to transmit Zika, right? So two different species of mosquitoes can't both transmit something equally well because their chemistries, they look the same to us, but their internal physiology and chemistries are very different. So basically HIV does not survive in the mosquito gut, so they just don't reinject it into you. And
good thing.
it is a good thing. And there are lots of herbs that are very effective. Again, I've had a student this summer looking at different ethnobotanical controls for mosquito at the larval stages, and she's found several plants that have promise.
Okay, one last question. Going once. Yes.
So I think years ago I read about some research that was funded by the Gates Foundation where they take the genes of mosquitoes and then it takes 2 generations. Basically it makes the mosquito not be able to reproduce, and it's a way to wipe out a whole species. What's your opinion on that? Is that a good idea or a bad idea?
So my opinion is it's not a bad idea, right? So because when they target it genetically, they can actually target a species. Wiping out 3,500 species of mosquitoes is not a good idea. Wiping out 70 species is not a good idea. Wiping out Aedes aegypti, might not be a bad thing. I wouldn't want to pull the trigger on it, but I don't have a huge issue with targeting it with genetics. The problem is that super expensive, and it may be very effective for islands or places where you could actually really release enough to make a difference. But so the idea is that they release these genetically modified male mosquitoes, and they breed with the females, and then their offspring are not reproductive. So you have to release enough male mosquitoes in enough places to outnumber all the other male mosquitoes that are already there. And then they only live a little while. Males don't even live that long. They tend to be kind of small and weak, and they don't live as long as the females. And so the numbers you have to release and the number of times you have to release them make it something that may be effective on an island or for really severe outbreak, but right now the technology doesn't look like it would be effective for the kinds of urban mosquito issues that are
The
growing.
way they described it would be a recessive gene, so that when the male mated, then it would generate a large population of children, basically, that would then
go. Yeah, and there are some more aggressive genetic modifications that don't just pass on half of the gene, they pass on to all. And those things, again, so the other thing that I talked about, a lot of these species don't move more than maybe 100 meters tops. And so we have to release these every 100 meters. It's promising, but in very specific spatial situations, I think.
Okay, well, I would like to thank you all for coming and for your excellent questions. And I would like to thank Shannon for that very stimulating and kind of scary.